Welcome to this final fifth video for the lecture 3 notes in terms of just some of the problems that we didn't have time to discuss in class from these lecture notes. So these are some of the stuff from chapter 4. That's kind of all that remains that wasn't covered in the other videos. And they're not long proofs. You can see I'm providing scratch work in 410. That's a few lines long. It's 3 lines long. In 415, it's 3 lines long. A few more lines in 416. So just a few comments here. 410 says, hey, if a number is greater than 0, then there's got to be a natural number such that 1 over n provides a lower bound for a plus than a, and n is greater than a. Okay, simple enough. What you can rephrase that as saying a has to be in the interval 1 over n to n, and it's not either of the endpoints. There's got to be some n for that because these inequalities are strict. So the basic scratch work is this: like, if I'm actually doing this in a different way. We started with sequences and limits. I actually want to use those to do the proof. If a is greater than 0 and 1 over n converges to 0, I can use a like epsilon, which means I can actually choose an n1 such that 1 over n1 is less than a, right? So I say, okay, I'll do that because I know 1 over n converges to 0. If a is greater than 0, actually by a limit theorem, a over n is something that converges to 0 as well. It's this limit, you can go look up which limit theorem. So then it says, well, boy, then I can choose an n2 such that a n2 is greater than 1, or excuse me, less than 1. And that would mean that a is less than n2, just a little bit of algebra, multiplying 2 over. Guess what you choose n to be? The max of n1 and n2. Big surprise. So, okay, you can write that in a nice proof, but those are the details. 415, you have, hey, 2 numbers a and b, and you're saying if a is less than or equal to b plus 1 over n, for any counting number that I pick, any natural number, then a had to be less than or equal to b. So in other words, you could say what this is saying is that we know b is a lower bound for this set. And in some sense, we're saying if a is any other bound for that set, b is the greatest lower bound. Okay, again, I just go through arguments using sequences. If a is less than or equal to b plus 1 over n, that means a minus b is less than or equal to 1 over n, and then 1 over n goes to 0. And then I can, when I pass the limit, that means that a minus b is less than or equal to 0. Then you can go look up this exercise, and then I add the b over. Not so bad. I didn't end the proof. There's my end of the proof, but I'll erase that. And 416, if this show that the sup of the rational numbers that are less than a is equal to a for any real number, whether that number is rational or not. So, all right, let a be an r and epsilon be greater than 0. By definition, a is an upper bound for that set, right? Because you're saying a is greater than everything that's in the set, because this is the set of numbers where a is greater than them. So a is some upper bound. So a minus epsilon is something that's less than a, and it can't be an upper bound. Or excuse me, I didn't say it's the least upper bound yet, but it's less than a. But I can find rational numbers by the denseness argument that are between a minus a and a. Go look up the denseness argument, and or look up what the denseness of Q and R is. This is in section 4. So that means that there's actually a number, some s, that's in this set that has this property that it's between a minus epsilon and a. And that means that a minus epsilon is not an upper bound for this set. And that means that a is least upper bound, because this is true that epsilon is arbitrary. So that's it. These are some pretty easy problems. But if you want some additional practice with just proofs and soups and imps a little bit, you can play with these problems or read them and take them a little more carefully. So that's it, short video, and that's the last one I'll be making for this set of lecture notes.